Hello, this is Meteorology 113, Lecture 9, Particulate Matter and PM2.5. This is the third lecture of Course Module 3, Outdoor Air Pollution, Ozone, and PM2.5. The outline of this lecture is as follows. We will first give an overview, where we will summarize fine particulate and briefly summarize the health concerns of fine PM exposure. More details on health effects will be provided in Module 4 during our study of air pollution epidemiology. We will also look at concentration patterns and the attainment status of PM2.5 pollution locally, across the U.S., and globally. We will then go into further details on PM composition. We will distinguish between PM10, PM2.5, and ultrafine particulate, highlighting the compositional aspects of each. We will also distinguish between primary versus secondary PM2.5. We will then conclude by briefly describing main emission sources of PM generated by combustion sources. Fine particulate air pollution. Overview. We begin with a basic description of particulate air pollution. There are several terms used to describe this. Broadly, the name particulate matter, or PM, describes particles in the air that are so small that they stay suspended in air, and therefore are able to blow in the wind, much like it were a gas. Large particles, instead, would be heavy enough to not stay suspended and therefore would settle to the ground due to gravity very soon after being emitted. The precise particle sizes associated with PM pollution are illustrated by the graphic shown below. Since these particles are small in size, we generally refer to particle sizes of PM in micrometers. 1 micrometer is 1/1,000,000th of a meter and 1/1000th of a millimeter. A common upper bound of particle size where particles stay suspended in air is 10 micrometers in diameter. We call the mass concentration of PM pollution for particles smaller and up to 10 micrometers PM10. Likewise, we call the mass concentration of PM pollution for particles up to and smaller than 2.5 micrometers PM2.5. Both PM10 and PM2.5 are among the criteria air pollutants, where ambient air concentration standards exist. To get an idea of the size of 10 and 2.5 micrometer particles, it is common to reference this to something more familiar, like a human hair. This is indicated on the graphic. The typical width of a human hair is between 50 and 70 micrometers. Also shown on the graphic are grains of beach sand at about 90 micrometers in size. Overall, 50 to 100 micrometers is similar to the size of fog droplets and small raindrops. 10 micrometers, the rough upper bound of suspended particulate respirable to the human lungs, is therefore about 1/6 the size of the width of a human hair, and PM2.5 is even smaller than this, around 1/20th. PM10 and PM2.5 are therefore very tiny particles. PM10 and PM2.5 air pollution is therefore comprised of very tiny particles, as I just said. They stay suspended in air and can travel long distances in the wind. PM2.5 is also so tiny it can penetrate deeply into lungs and cause adverse health effects if inhaled. More details on these definitional matters I provided on this slide. PM are aerosols, a term we introduced back in Lecture 1. Aerosols are particles that stay suspended in air. Since the precise size of PM particles is so important, it is useful to give a better idea of what we mean by particle size. By particle size, for example, a particle size of 2.5 micrometers, we are referring to the diameter of a spherical particle. PM particles, however, are generally not spherical, as we will see in electron microscopy images on a later slide. Therefore, one needs to imagine a non-spherical particle morphed into a sphere in a manner where the overall volume stays the same. This is shown on the graphical inset. The actual particle shown by the solid line, and the imaginary spherical one of the same volume by the dashed line. A more precise technical definition of particle diameter is aerodynamic diameter. Details on this can be read about on the Wikipedia page web link below for those interested. The size of PM particles directly relates to health impacts, since the smaller the particles, the more deeply they can penetrate into the lungs. This graphic illustrates this. As we mentioned a couple slides back, 10 micrometers is a rough size up to and below which particles are suspended in air and inhalable. Recall the term PM10 as all particles less than or equal to 10 micrometers in diameter. Referring to the graphic, once inhaled, the larger size fraction of PM10 is more likely to be captured in the upper respiratory tract, the nasal passages and throats. This can cause respiratory irritation and generally short-term health problems. However, more serious longer-term health impacts are felt due to the smaller particles. Specifically, the PM2.5 fraction can penetrate through the upper respiratory tract into the lungs, irritating lung tissue. Even more dangerous impacts are for smaller particles, PM1, 1 micrometer or less, which can penetrate all the way to the alveoli, the tiny air sacs terminating bronchioli that reach the blood-air barrier. There is even evidence of these tiny particles passing into the bloodstream, causing more systematic chronic health effects. We will learn more about this in Module 4 when we study the epidemiological research of PM health effects. Particles less than 1 micrometer are termed ultrafine, which are the most dangerous. In general, the smaller the particle size, the more dangerous the associated health effects. Further reading on PM health effects is provided in these links. As mentioned, we will also cover this topic in more detail in Module 4. As mentioned earlier, PM10 and PM2.5 are both criteria air pollutants, and therefore have ambient air standards. These are listed here. Notice that both short-term, 24-hour, and long-term, annual standards exist. Note also that the annual standards are lower in concentration threshold value than the 24-hour standards. For example, for PM2.5, the 24-hour standard is 35 micrograms per meter cubed, while the annual standard is less, 12 micrograms per meter cubed. The standards are therefore designed to be protective of short-term, high daily episodic exposure that can cause acute health effects, and lower concentration sustained exposure that can cause chronic health effects. The current attainment status of PM2.5 ambient air quality standards across California is shown on this slide. The different color shadings indicate air districts with serious versus moderate non-attainment. On the left, the attainment status for the 24-hour standard is shown. There are 5 air districts in non-attainment of the 24-hour standard: the Bay Area, Sacramento, the San Joaquin Valley Air District, Los Angeles Air District, called the South Coast Air Quality District, Air Quality Management District being the agency regulating it, and the Imperial Valley. On the right is the situation for the annual standard. There are 3 air districts in non-attainment of the annual standard: the San Joaquin Valley, Los Angeles Metro, and Imperial Valley. Non-attainment is therefore more widespread, with some serious non-attainment districts in California for the short-term standard. This is because of episodic periods when meteorological stagnation events during winter occur, which can cause short-term periods, days or perhaps weeks, of very poor PM air quality. However, areas where sustained exposure to poor PM air quality also exist. The San Joaquin and Imperial Valleys are both agricultural valley settings prone to poor PM air quality. Los Angeles, due to its size, multitude of emission sources, and unfavorable geographic setting, is also prone to sustained high PM concentrations in certain areas of the air district. A map of current measurements of annual averaged PM2.5 concentrations across the U.S. is shown on this slide. The symbols are colored according to concentration ranges, as shown on the legend. As seen, much of the country has maintained PM2.5 concentrations less than 10 micrograms per meter cubed, complying with annual standards of 12 micrograms per meter cubed. Areas of higher PM2.5 are indicated on the plot. However, for example, in the California Central Valley, as discussed in the last slide, and also areas of the industrial Midwest, where sulfate PM2.5 is common. We will discuss this in more detail in later slides. Notice also the higher values in Mexican cities, where emission controls are less stringent. Mexico City, in particular, has very poor air quality due to its size and unfavorable setting, surrounded by mountains. A map of current measurements of annual average PM2.5 concentrations across the world is seen on this slide. The symbols are colored according to the concentration ranges, as shown on the legend. As seen, very high annual PM2.5 concentrations exist in China and India. This was something students in this class learned about on the last assignment, where videos of the situation in India and China were viewed. Several other areas of high concentrations are seen in Eastern Europe and across major cities in the developing world. Again, rapid growth, industrialization, and motor vehicle use, coupled with the lack of emission controls, leads to this situation. Fine particulate air pollution. Composition. Electron microscopy is a commonly used scientific measurement technique for viewing very small objects not detectable to the human eye. A web link for those interested in learning more about the technique is provided below. The electron microscopy image on the right of an ant illustrates the fine detail obtainable from this technology. Electron microscope images of various individual fine particulate aerosols in the ambient air pollution environment are shown on this slide. All of the particles seen here are around 1 micrometer in size or less. There are size bars on each image for the viewer to gauge precise sizes of each particle shown. The level of detail of the images is impressive. More substantially, one sees the variety of shapes and types of fine particulate aerosols that can exist in a given sample of air. These can be almost perfectly spherical, for example, for the organic carbon seen on the middle top of the slide, and the smoke conglomerate particles on the lower right. The individual soot particles shown on the lower right is part of branches of a conglomerate of particles comprising a smoke aerosol. Other particle types seen are ash on the top left, ammonium sulfate on the top right, a form of secondary particulate as we will discuss later, and mineral dust on the lower left. The variety of particle shapes, sizes, and composition in the fine PM mix make the subject of understanding and characterizing fine PM a challenging task for air pollution researchers and regulators. Much is still to be learned of how PM health effects depend on the composition of PM. Since different types of PM arrive from different emission sources, understanding PM composition is important for regulating PM. A chart of PM composition organized according to particle size is shown on this slide. The particle size on the horizontal axis ranges left to right from sub-micron size all the way out to sizes greater than 10 microns, not associated with PM air pollution. Various types of particulate are shown on the body of the graphic, with the length of the red line underneath each spanning the approximate range of particle size associated with each type shown. We can mark off the PM10 and PM2.5 ranges within this graphic. Note that both PM10 and PM2.5 include particulates smaller up to the indicated size. Hence, we mark off each with a box spanning the entire range smaller and up to the size of each. Within the PM10 range, one can summarize the composition according to three main classes. First, the larger size portion of PM10 is comprised of dust. This generally comprises any fine dust, soil, crustal material, large ash, or char. Such material generally originates naturally from windblown dust or anthropogenically from construction, mining activity, road dust, close to large fires, or other manners. Second, the smaller size portion consists of combustion particulate. This is smoke, soot, or other carbonaceous, carbon-containing particulate from any combustion source, such as fires, motor vehicles, or industrial fuel combustion sources. Third, there is a class of fine particulate called secondary particulate. We learned about what a secondary pollutant is in the last lecture when explaining ground-level ozone, which is not emitted directly but is formed from precursor NOx and VOC emissions. Ozone is therefore a secondary pollutant, not directly emitted but formed photochemically from other emissions. Likewise, there are PM aerosol types that are secondary. These include sulfates, nitrates, SO2 mist, secondary organic aerosols, and others. The formation process of these is complex and will not be covered in great detail here. However, as with ozone, precursor gas emissions are associated with each of these secondary aerosols. We will cover this shortly. Finally, note that the types of particles that are not included in PM10 are larger in size. This includes coarse dust generally greater than PM10, pollen and sand, and other similar types of particles. While not technically part of PM10 and PM2.5, pollen, of course, causes health problems and allergic reactions, and is of concern for this reason. Shifting over to PM2.5, we see that dust is largely eliminated from the composition mix, leaving combustion particulate and secondary particulate. When talking about the very small particle sizes that can penetrate deeply into lungs, we therefore are not too concerned with dust. Rather, combustion and secondary PM are of most concern with respect to PM2.5 and more hazardous smaller ultrafine particulate. So summarizing, when referring to PM2.5, there are two main classes of composition types. First, there is combustion PM2.5. It is fine particulate emitted directly from combustion sources, tailpipes, smokestacks, etc., and is therefore primary particulate, emitted directly. Most of this is submicron particulate, less than 1 micrometer, and therefore able to penetrate deeply into lungs. The third bullet indicates various types and names given for combustion PM2.5. Most familiar to students in this class is smoke and soot, which we see emitted from combustion sources as black smoke. The other names, black carbon, elemental carbon, organic carbon, tar, and etc., are terms used by air pollution professionals to be more precise about chemical makeup and of various combustion PM types. In this class, we will just refer to all of these collectively as combustion PM2.5. Second, there is secondary PM2.5. This is fine particulate not directly emitted from sources, but rather formed from chemical reactions in the atmosphere from other pollutant gases that are emitted, similar to ground level ozone studied in the last lecture. The pollutant gases that are emitted that chemically form into secondary PM2.5 are called precursors. Like combustion PM2.5, secondary PM2.5 are very small submicron particles that penetrate deeply into lungs. Among the main types of secondary PM2.5 are nitrates, sulfates, and secondary organic aerosol. A bit more detail about secondary PM2.5 is presented on this slide. We distinguish three broad types: nitrates, sulfates, and secondary organic aerosol. For each, we indicate the main precursor gases involved in its formation and a summary of the formation mechanism. Nitrates are formed from emissions of nitrogen oxides. Ammonia gas also leads to a particular type of nitrate called ammonium nitrate. Nitrates form from aqueous chemistry and therefore favor a high humidity environment. Sulfates are formed from emissions of sulfur dioxide and other sulfur gases. Ammonia gas also leads to a particular type of sulfate called ammonium sulfate. Sulfates also form from aqueous phase chemistry and therefore favor a high humidity environment. Secondary organic aerosol form from emissions of volatile organic compounds. They form from photochemical reactions involving sunlight, similar to ground level ozone. SOAs therefore prefer hot, sunny weather. Little is known about the details of secondary organic aerosols, so we will not cover these further in this lecture. Focusing on nitrates and sulfates, the next few slides give an overview of the aqueous chemistry that leads to their formation. Seen here is a graphic where the process of emissions of precursor gases through the chemical formation into nitrate and sulfate particulate is pictorially summarized. Tracking this process, we see on the bottom left emission sources of precursor gases. These include industrial, stationary, mobile, and agricultural sources. These emit the main precursor gases, SO2, NOx, and ammonia, and other compounds that can play a role. Once in the air, these precursor gases, in the presence of high humidity, can chemically react to acidic compounds, which in turn dissolve and dissociate into ions in liquid water in the air, haze, fog, mist, cloud droplets, etc. The hydrogen ions produced during dissociation of these compounds into these drops leads to increased acidity of fog, clouds, and rain. This is the cause of the acid rain, which students may be familiar with. The ions of nitrogen and sulfur produced in this way then combine into solid particles with various other ionic species in the air or within the droplets to form tiny particles, which we call nitrates and sulfates. For example, the combination of negative nitrate and sulfate ions with the positive ammonium ion leads to ammonium nitrate and ammonium sulfate. These particles can exist as a mist, containing some liquid water around and within the particle, or dry, without H2O, remaining left behind in the air after the cloud, fog, or haze droplets evaporate. Given this summary of PM2.5 composition, we can now look at some examples of the compositional mix of PM2.5 in air samples. This is called PM2.5 speciation in the air pollution professional world. We show on this slide two examples for California on high wintertime PM2.5 days. On the left is a sample from the San Jose 4th and Jackson air monitoring site, and on the right from the Bakersfield, California Avenue air monitoring site in the southern San Joaquin Valley. The way to interpret these is to imagine collecting a sample of PM2.5 particulate, sending it to the lab to distinguish the chemical makeup of the particles in the sample, classifying these individual chemicals into various chemical groups, and presenting the results on a pie chart. Looking at those presented here, we see that the samples are predominantly made up of combustion particulate and secondary particulate. In San Jose, the proportions of each are roughly equal, a little over half combustion PM2.5 and a bit less than half secondary PM2.5. Combustion particulate shown here in the light blue and black, and the secondary PM in the red and the yellow. In Bakersfield, a larger percentage is nitrates, with much but lesser amounts being combustion particulate. These charts are illustrative of the complexity of PM2.5 speciation and the variations that can occur from site to site. The speciation of PM2.5 is important for air pollution regulators, since this chemical makeup of PM2.5 then indicates which emission sources to prioritize in developing regulations to reduce emissions and concentrations of PM2.5 in the air. Highlighting again the conditions for poor wintertime PM2.5 in California, we again emphasize the importance of high pressure systems and stagnation events. We revisit a graphic from Lecture 7 of a particular recent event. The weather map shown on the left is a broad area of high pressure covering the western US and California. Meteorologically, this leads to very weak winds and low dilution of emissions, cold temperatures, the presence of ground-based temperature inversion layers, and high relative humidity and fog. The effects of this on PM2.5 are high episodic PM2.5 events, with both combustion and secondary PM components in their makeup. The primary combustion PM2.5 results from smoke emitted from residential heating, often wood smoke from people heating their homes, and normal stationary and mobile combustion sources. The secondary PM2.5 is mostly nitrates, with the precursor NOx emissions from mobile and stationary sources and ammonia from agricultural emissions, largely fertilizers and livestock. Until the high-pressure system breaks down, these conditions persist, leading to increasing buildup of PM2.5 pollution over days. Stagnation periods unfortunately usually last several days or even perhaps beyond a week. We mentioned the California Central Valley, primarily the southern San Joaquin Valley, as a region where wintertime PM2.5 is high. We see here a graphic of this to highlight details. On the left is a photograph of the familiar Thule fog of the Central Valley. This is the ground-based fog that forms during periods of cold, clear sky conditions. The fog is contained within a shallow, ground-based temperature inversion, where cooler air settles near the bottom and warmer air rides the top. The conditions of cold air and high humidity favor nitrate PM2.5. Agricultural emissions of ammonia and abundant NOx from trucks traversing the valley, seen on the photograph on the right, provide the precursor emissions for nitrates and ammonium nitrate. Also, trucks emit abundant combustion PM2.5 directly. A subclass is diesel particulate, emitted from combustion of diesel fuel within diesel engines. It turns out that long-term exposure to diesel PM is particularly harmful with respect to increased cancer risk. We now turn to another region, the U.S. Midwest. Shown here is a graph of PM2.5 speciation for sampling at Pittsburgh, Pennsylvania, over roughly a 2-year period. Each bar along the horizontal is a particular month over the 2-year period, and the bars are hatched according to the PM2.5 compositional makeup. The vertical axis is the monthly average PM2.5 concentration in micrograms per cubic meter. The main thing to notice, which distinguishes these samples from those in California presented earlier, is the relative abundance of sulfate PM2.5, the green portion of the bars. Also different from California, the highest concentrations occur in summer months, mainly due to increasing importance of sulfates in the speciation mix. This is because the high humidity environment required for secondary sulfate aqueous chemical formation occurs mostly in summer due to humid airflow from the Gulf of Mexico. Combustion PM2.5, indicated by the red as organic carbon, is fairly constant throughout the year by comparison. The reason for the higher sulfate proportion in PM2.5 in the U.S. Midwest is because of the presence of many coal-fired power plants, which emit much precursor sulfur dioxide. This is highlighted on this slide. The bubbles on the map are coal-fired power plant locations. The larger the bubble size, the greater the energy producing capacity of the power plant. The coloring of the symbols is according to the dollar cost per kilowatt hour of electricity production. These details don't need to be known for the upcoming quiz. To recall, the town of Denora, where the major air pollution event in 1947 occurred that caused deaths and motivated the Clean Air Act, is close to Pittsburgh, about 100 kilometers or so to the south. The haze of summertime sulfate PM2.5 in Pittsburgh is seen on the bottom photograph on this slide for a particular day. PM2.5 concentrations were 45 micrograms per meter cubed on this day of the bottom graphic. By comparison, a clean day, 4 micrograms per meter cubed, is seen on top. Fine particulate air pollution, emission sources of combustion PM. We conclude this lecture with some photographs that highlight some aspects of combustion PM emission sources. As seen in these images, this is largely black smoke emitted from combustion sources. Its black color is a consequence of the absorption of all visible light wavelengths, and therefore a black color results. Recall that although the visual may imply these are large particles, since they are so dark and black, the particles emitted by these combustion sources are extremely small, ultrafine submicron particles. They are therefore very harmful if inhaled. Also recalling from our study of combustion physics from an earlier lecture slide set, smoke results from incomplete combustion. Smoke is therefore comprised of unburned or partially burned fuel constituents. Chemically, the makeup can be as simple as pure carbon, called elemental carbon, or a complex mixture of tar and other organic compounds, called organic carbon. The chemical makeup of combustion PM and its effects on health is actively being studied by researchers. From this research, it is being found that diesel smoke emissions, largely from trucks, are a particular harmful carcinogenic form of combustion PM2.5. California regulators are taking active steps to reduce particulate emissions from trucks, phasing in engine retrofitting so engines are modernized and have advanced emission control equipment. Also, cleaner and lower sulfur-containing diesel fuels have been developed to reduce particulate and precursor gas emissions from diesel engines. Another main source of combustion PM is biomass burning. This can come in the form of natural wildfires, an example seen from a photograph of our recent October 2017 Napa Valley fires in Northern California. Another example seen on the right is agricultural and forest burning, which is often done to clear space for agricultural crop production and/or to dispose of waste biomass. Aside from being a hazard to human health if inhaled, particulate emissions from these sources span large areas and can therefore inject particulate deep into the troposphere and be transported long distances across the globe downwind. Biomass combustion is therefore of concern for long-range global transport and is an important contributor to the global particulate levels affecting climate change.